On this video, we're going to talk about complex numbers. These are the famous I. So historically, it comes from trying to solve the equation x squared plus 1 equals 0. So mathematicians hundreds of years ago were really obsessed with solving equations, and it was really bothersome that something as simple and straightforward as x squared plus 1 equals 0 didn't have a solution with the real numbers. So it was thought at that time that all numbers were either positive, negative, or 0. Those are the real numbers. And none of those is going to work because a positive times a positive is positive, and a negative times a negative is positive, and 0 times 0 is also 0. So none of those work. So the question became, and people weren't really sure initially, is there some other kind of number out there besides positives, negatives, and zeros? And so it's kind of imagine there was a number that was equal to the square root of -1, which is what we want to solve this equation. And so it was uncertain at first, and that's kind of led to the name. And so this is called the imaginary number. But it's accepted now, so there's not really any doubt about it. And I'm told that in electrical engineering, there are applications that require the use of the imaginary number I. So that's where it comes from. So we know that our square root of -1 is equal to I, and that means I squared is going to be equal to -1. We'll come back and talk more about that in a few minutes. The standard form of a complex number. So we take this number I and we throw it in the mix with all of the other real numbers. And so we get numbers like 3 plus 2i, or we get something like 5 minus, say, the square root of 2 times I. So these are all still complex. They're called complex numbers. Anything in the form a plus bi, where a and b are real numbers, is a complex number. So that is the complex numbers. And just as we have a special symbol for the real numbers, double bar R, there is one for the complex numbers. It's a C with that vertical line that is a little bit offset. So it sort of looks like a cent sign, but it's done with a capital C, and that vertical line doesn't go right down the middle. It's off a little bit to the left. So that's the set of complex numbers. So that means it's everything of the form a plus bi, where a and b are real numbers. So in particular, all real numbers are also complex numbers because b could be 0. So 3, e, pi, -7, square root of 3, those are all part of the complex numbers. So are what are known as pure imaginary numbers. Pure imaginary numbers are numbers where the a is 0. So those are going to be things like 2i, -5i, pi I, there's a number for you, and so on. So let's see, we should also talk, maybe before we get into the arithmetic with complex numbers, we have an issue that we kind of need to resolve. We know that, for example, the square root of -12, we can think of as the square root of 4 times the square root of -1 times the square root of 3. The square root of 4 is 2. The square root of -1 we've decided is I, and so we would simplify that to be 2i square root of 3. We know that when you multiply, say, two numbers in radicals, a square root of 2 times a square root of 3, we can multiply their radicands, that's called the thing inside, and you get square root of 6. So this poses a potentially troublesome idea here, because on the one hand, you could say, well, we're going to do like we did with the positive numbers and say that's going to be the square root of -2 times -3, which would be square root of 6. On the other hand, somebody else might say, well, I'm going to simplify square root of -2 and call it I square root of 2, and simplify the square root of -3 and call it I square root of 3. And a person that did that would get I squared times the square root of 6, which would be a negative 6. And we know we can't have two different answers to the same problem, so one of these is correct and one is not. And so this is the correct order of operations when you are simplifying or multiplying radicals. If you have that negative inside the radical, you have to bring it outside the radical as I before you do multiplication. The rest of it is pretty straightforward. Well, most of it. So 2 plus 3i, there is going to be one imaginary number, a complex number. And if you add that to 3 minus 7i, you would do it just like an Algebra 1 student would. You just combine like terms. So you combine the real parts, the 2 plus 3, to get 5. And you combine the imaginary parts. 3i minus 7i is a minus 4i. And that's our answer. In a similar fashion, if you had something, complex number minus another complex number, just remember to distribute that minus sign and then combine like terms. So that would be 3, let's see, the 3 minus 1 would be 2, and the negative 4i, it would become a plus 3i, would be a negative I, and that would be our answer. When we multiply two complex numbers, we do the distribution thing, and then we combine like terms and simplify I squareds. So that's going to give us 8. That would become an 8i. That would be a negative 6i, and that would be a negative 6i squared. So the I squared is negative 1, so the negative 6i squared would become the real number, positive 6, which we would combine with the 8 to make 14, and the 8i minus 6i would be a 2i, and we get another complex number. So in the language of math, the complex numbers are closed. When you take a complex number and add to it another complex number, or subtract it, or multiply it, what you get is still going to be a complex number. Okay, we're going to save the division thing until after we talk about complex conjugates. So with the idea of complex numbers, we need to have this understanding of what are called complex conjugates. So if we have any complex number a plus bi, we write this symbol x with a bar over it, and that is read as the complex conjugate of x, complex conjugate of x. And what it is it leaves the real part the same, and it changes the sign of the imaginary part. That's a complex conjugate. So, for example, if we had 2 plus 5i, its conjugate would be 2 minus 5i. If we had 3 minus 4i, its conjugate would be 3 plus 4i. If we had, say, just the number negative 2, we could think of negative 2 as being negative 2 plus 0i, and so its conjugate would be negative 2 minus 2i. It'd still be the same thing. So the complex conjugate of a real number is itself. And if we had, say, a pure imaginary number, we could think of that as being 0 minus 3i, and so its conjugate would be 0 plus 3i. So in the case of a pure imaginary, its conjugate is the opposite of the original. Does that kind of make sense? Now there's some kind of interesting things that happen. So when you take a number and multiply it by its conjugate, then we're going to end up with something that doesn't have any imaginaries at all. So if you recognize that as a difference of two squares, that's what I would hope you would see. It's going to be the first term squared, 9, and then minus the second term squared, and what we get from the distribution, the negative 6i and the positive 6i will cancel each other out, and so interestingly enough, you get a pure real number, a real number. So any complex number times its conjugate is going to give you a real number, which leads to a new way now of factoring something that you can't factor using only real numbers, but you can factor using imaginaries. So if we know that, if we remember that x squared minus 4 we call the difference of two squares, and that would factor into x minus 2, x plus 2, we can treat x squared plus 4 as the difference of two squares using imaginaries, because you can see that when you multiply the negative 2i times the positive 2i, that will be a negative 4i squared, which is going to be a positive 4. And the 2i times x and the negative 2i times x will cancel each other out. So it's a new way of factoring something over the complex numbers that is irreducible or prime, cannot be factored over the real numbers. So one more shot at that. If we had something like, say, 4x squared plus 9, for real numbers, that will factor into 4 plus 3i times 4, or 4x plus 3i minus 4x, or times 4x minus 3i. All right, let's talk about some powers of I. So we know that anything to the 0 power is 1, and we know that I to the first is I, and that's our square root of negative 1. We said I squared is negative 1, because that's the square root of negative 1 times the square root of negative 1, and that's going to give us the negative 1. I cubed we can think of as I squared times I. I squared is negative 1, so that becomes negative I. I to the fourth we can think of as I squared times I squared. That's negative 1 times a negative 1. Now we're back to positive 1, right back to where we started. And then it's going to just keep cycling, because I to the fourth, or I to the fifth rather, is I to the fourth times I. I to the fourth we just said was 1. 1 times anything is the anything, so we're right back to I. And similarly, I to the sixth we would think of as I to the fourth times I squared. I to the fourth is 1. I squared is negative 1. That's going to be negative 1. So this gives us a way of simplifying any power of I. If we have something like, say, I to the, we'll say 43rd power, we know that every power, every fourth power is going to be 1. So we could think of this as being I to the largest power of 4, largest multiple of 4 that we can. That power of 4, this part right here, is going to simplify, because we can think of that as I to the fourth to the 10th. I to the fourth we said is 1, and 1 to any power is 1. So what we get essentially is just I to the remainder of what we got when we divided this by 4. And then we can break this down into I squared times I, which is going to be negative I. So let's see it in another form. If we have I to the, say, let's go 33rd power. What we're going to do is divide 33 by 4. And so we can say 8 times 4 is 32. The remainder is 1. So this is going to be I to the 32nd, that's our 4 times 8, times I to the remainder. This I to any power of 4 is 1. Whoops. And so our answer then simplifies to be just I. I to the 33rd is I. Now, we can do that also with negative exponents. So I to the, say, negative 5 is 1 over I to the 5th. We can break that down and think I to the 5th is I to the 4th times I. I to a power of 4, to a multiple of 4, is 1. So that's 1 over I. Now, we don't want to leave i's in the denominator, so what we do is we multiply it top and bottom by its conjugate. So 1 times the negative I is negative I times negative I is negative I squared, which is just negative of negative 1, and so we get the negative I. Let's see that again. I to the, say, 21st power, negative 21st power, is 1 over I to the 21. That's going to be I to the 4 times 5 is 20. So that's I to the 20th times I. The I to the 20th is 1. So that's 1 over I. We multiply top and bottom by the conjugate of I. And that's going to be negative I over 1, or negative I. Kind of cool. Let's talk then now about division of complex numbers. So if we take division, if we had, say, 3 plus I divided by 2 minus 3I, we would just write that as a fraction. We'll show our division like this. So there's our complex number 3 plus I divided by the complex number 2 minus 3I. So what we're going to do is to multiply top and bottom by the conjugate of the denominator. So remember, 2 minus 3 is the denominator. Its conjugate is going to be what would make it the difference of two squares. That is, leave the first part, the real part, as it is, and change the sign of the imaginary part. And since we multiply by the same thing over the same thing, that's just multiplying by 1. So we're going to change its appearance, but not its value. Then we just do the arithmetic. 3 times 2 is 6. 3 times 3i is 9i. Well, I times 2 is 2i. I times 3i is 3i squared. Now the denominator works out very nice. That's going to be our difference of two squares, 4 minus 9i squared. Now we clean up. 3i squared is negative 3. That combines with 6 to become positive 3. 9i plus 2i is 11i. In the denominator, a minus 9i squared is a minus negative 9. That's a plus 9. That becomes 13. Now, this isn't wrong, but we are going to write it in the form a plus bi. So we will separate this into 3/13 plus 11/13 I. So there is our a plus bi. So again, we see that you start with a complex number divided by a complex number, and what you end up with is a complex number. Let's do one more. Let's do maybe, let's say 2 minus 5i, and let's divide that by 1 plus 2i. So we'll multiply, remember, top and bottom by the conjugate. So we change the sign of the imaginary part in the denominator. We multiply, so the 2 times 1 is 2. The 2 times 2i is a negative 4i. Negative 5i times 1 is a negative 5i. And negative 5i times negative 2i is a 10i squared. In the denominator, we get the difference of two squares, the first one squared minus the second one squared. We clean up. I squared is negative 1, so this becomes negative 10. We combine it with the positive 2 and get negative 8. The negative 4i minus 5i is a minus 9i. In the denominator, we're going to get a 1, and then a minus 4i squared becomes a 1 plus 4. That's going to be 5. We'll split this up and call it negative 8/5, and that'll be a minus 9/5 I. So there is our complex number in a plus bi form. All right, very good.